Hi, I'm Mr. Taru. In this video, we are going to learn 3 different ways of proving that 2 triangles are similar, and continue our lessons recently that we just had for relearning or being introduced to ratio and proportions, and then working with equal ratios to find missing sides of similar polygons. That was the last video. Well, now the similar polygons that we're dealing with specifically are going to be triangles, but before we start setting up equal ratios or proportions to try and find missing lengths of these triangles, we must first actually prove that they're similar. First way of doing this is going to be the angle-angle similarity postulate. And it says if 2 angles of one triangle are congruent to 2 angles of another triangle, then those 2 triangles themselves are similar. Remember, that's same shape, but they can vary in size. If they're the same size and shape, we're going to say that they're congruent, like we already have in our class. So we have 2 triangles here. We have triangle ABC is similar to triangle DFE. You need to make sure that your corresponding angles are congruent, just like we proved that 2 triangles are congruent. And we see that angle A and angle D are congruent, so it's one pair of congruent angles. And angle C and E is also congruent. Remember that when we just studied similar polygons, the first condition was for 2 polygons to be similar, all of the angles had to be congruent. All the corresponding sides had to be proportional in size as well, but that first condition was all of the angles had to be congruent. And that kind of automatically happens in your 2 triangles. If you have 2 pair of angles which are congruent, you only have 1 pair of angles left, and the inside, the sum of the interior angles of triangles has to be 180 degrees. So if these 2 angles are the same, and if these 2 angles are the same, then automatically angle B and F are going to have to be congruent as well, because those 3 angles have to add up to 180 degrees. Let's use that AA postulate here and show that these 2 triangles are congruent, or excuse me, similar. They have a different size. Now, none of my angles right now are being marked as congruent. We're going to assume that we don't have a separate segment of AC and CE and BC and CD. I mean, they are segments, but we're going to be looking at BD as an entire continuous segment and AE as being a continuous segment, so that we can actually do this problem. Now, when you have 2 segments or lines intersecting, the angles on the opposite sides of that intersection are going to be congruent. They're called vertical angles. So angle ACB is going to be congruent to angle DCE because we know that, let's pick a different color, that our vertical angles are always congruent. So boom, I just got 1 pair of congruent angles due to vertical angles are congruent. What else do we have going on here? Well, we have a mark here that says that segment AB is parallel to segment DE. Now, we talked about parallel lines many chapters ago now, but we still can't forget all those definitions and properties. And one of them said that if you have 2 parallel lines being cut by a transversal, and usually you get kind of like a zigzag shape or a Z shape when that happens, that the alternate interior angles are going to be congruent. So I actually have enough now. I have 2 pair of congruent angles inside these triangles to say that these 2 triangles are similar. Now I'm going to give you the statement of these names here in a second. You see how I'm justifying why these angles are congruent as I go through the problem? I'm basically verbally doing a 2-column proof. That's why we stress those proofs with you so much. And we still do. Haven't been doing so many in these videos as I was, but that's why we stress those videos so much as we build our skills of geometry. As I just effectively did a 2-column proof with you there verbally. So though you don't see me maybe writing as many 2-column proofs as I was, and maybe you're not doing them in your class so much, you're still doing them in your head. Otherwise, how do you do this problem? Okay, at any rate, I want to say that these 2 triangles are similar. I'm just going to randomly say that this triangle over here is triangle ABC. Now when I go to, again, name my similar triangle, I have to remember, just like with congruent triangles when I was proving those, that I keep these angles, these corresponding angles in the same order. So angle A in this triangle has not been marked as a congruent pair, but it is, but there's no mark in it yet. So we see that A matches up with angle E. That the next angle I have identified in my first name was B. Well, angle B is congruent to angle D, so D, and then there's only one left of C. So triangle ABC is similar to triangle EDC due to AA. Over here, we have another, we have another example. We have two right triangles. We have, of course, one pair of congruent angles already because they're both right angles, and all right angles are 90 degrees, and thus they're automatically going to be congruent. But I have 19 degrees and 71 degrees identified. Well, the interior sum of a triangle has to be 180 degrees. So if I take 180 degrees and I subtract 90, and then I subtract 71, if this angle right here is also 19 degrees, well, and it is, then again, due to AA, a pair of angles congruent here and another pair here, then these two triangles are also going to be called similar, or they're similar triangles due to the AA postulate. Okay. Now, let's not forget that congruent C is a form of similarity. All you need for two triangles to be similar is that they're the same shape and may vary in size. I don't have any marks on the lengths of these triangles. I've drawn them to look like they're a different size, but you can never draw, you can never trust the scale of a drawing. You can only trust the information given to you in that diagram. So these triangles may very well be exactly the same size, but I do know they're the same shape, and that's why they're similar due to the AA postulate. Side angle side, or let's get sassy. You saw this same orientation of letters when you were proving two triangles were congruent. But instead of these two pairs of sides being congruent, well, let's see what it says. If an angle of one triangle is congruent to an angle of a second triangle, so we have a pair of congruent angles, sounds a lot like when we were proving triangles congruent, and the sides that include the two angles are proportional. See, when we originally did the side angle side theorem, these two pair of sides that included the angle had to be congruent or equal themselves, but now it's proportional. Then the triangles are congruent. So we have two triangles here drawn again, kind of purposely showing a different size. I've got angle A and D being marked off as being congruent. Now I guess I could have included numbers here, but if we have the two sides that include that angle that's being identified as being congruent, if those pairs of sides are proportional, that means that if I do AB divided by DF and if I do AC divided by DE, keep the division that you're setting up in the same order. So as we can see over here, I've gone left to right for the sides of AB and DF, and I've gone left to right as I've set up my fractions to look at the proportions. If those two proportions are equal, then these two triangles are going to be similar. So again, it's side angle side. You have heard that before. It was for proving two triangles are congruent, but again, we're not saying that we have two pairs of congruent sides. We have two pairs of congruent sides, which are equal, but now they are proportional. That's the difference between side angle side for congruency and side angle side for similarity. I've got one more theorem to give you, and then we're going to work through three more examples to finish this video. Next theorem that sounds like we're proving that triangles are congruent, but it's again similar. Side, side, side theorem. If the corresponding sides of two triangles are not congruent, but proportional, then they are similar. So I have our couple of triangles here drawn out, and as long as, again, I keep my as I set up my ratios or my proportions to make sure or check to see if they are similar, let's see here, we have AC over DF. So we're going AC to DF. So we're going left to right. So every single one, left to right, left to right, left to right, setting up those proportions to make sure that the two triangles are similar. Keep that order the same as you set up all your ratios, and if they're all equal, then you can state that those two triangles are congruent due to side, side, side. Okay, so we got three examples to finish up this video. Are these two triangles similar? Well, I don't know. We're going to figure that out. But we have two triangles in here that are nested together, and these two triangles are sharing a common angle. So we already know that there's one pair of angles which are congruent. If you can set up the problem this way, that's great. However, if you find it a little bit difficult to get these questions correct when you have triangles or polygons like in the previous section that are nested together, you may want to redraw it separately to make it a little bit easier to figure out. And so you don't have to watch me draw. Let's get that up here. There we go. What I've done, of course, is taken the two parts that make up the large triangle around the outside and did 15 plus 5 and got 20. I did 12 plus 4 and got 16. And here's our two triangles which we're trying to prove that are similar. Now we have a pair of angles which are congruent because, you know, basically the reflexive property. We have both triangles using that same one. And then remember, if the pair of corresponding angles that include, or sides, excuse me, that include the angle which is congruent, if they are proportional, then the two triangles can be proven similar due to side angle side. So let's check that. We have, let's do 15 over 20. And so I just went, you know, left to right, set up your other ratio the same way, 12 over 16. And are they equal? That's the question. Well, if I reduce them, well, in this case, if I reduce them, it's going to be the same. But you can't compare the value of two fractions. You can't relate which one's greater than the other unless, not necessarily if they're in their most reduced form, but if the denominators are the same. So we're either going to have to resort to making these both decimals and comparing them that way, but that's kind of the cheap way. So many of us are uncomfortable with fractions. We want to make sure that the denominators are equal, and then we can just look at the numerators. The bigger numerator is the bigger fraction when the denominator is equal. But these two numbers both have a factor of 5. So if I divide the numerator and denominator by 5, reducing this fraction, 15 divided by 5 is 3. 20 divided by 5 is equal to 4. Do the same reduction here. I'm not going to divide by 5, but 12 and 16 both have a common factor of 4. So 12 divided by 4 is 3. And 16 divided by 4 is equal to 4. And look, our two ratios are the same. We, I guess I kind of got off a little bit of tangent there about comparing, the values or size of fractions, but we do want to have the same denominator. We have the same denominator, and thus the numerators are the same. We're looking for similarity. The proportions are supposed to be equal, so these fractions, of course, should be the same. If they're not the same, then the two triangles are not similar, but we do have these two proportions being the same. So that means that, yes, these are similar due to side, angle, side. Now, I guess I kind of feel like I want to do another example. If, okay, so if I come back here and kind of erase this work for a second, just to do a bonus example. If I come back here and I state that, or I change the diagram, and I show that these two lines are parallel, would those triangles be similar? This triangle here, the small one, and this large one. Well, let's see. If you have two parallel lines being cut by a transversal, then the corresponding angles, the angles that are in the same relative position, in this case upper right, if two parallel lines are cut by a transversal, then those corresponding angles are going to be congruent. Now with this second example, I'm not redoing the same problem, I erased everything. We can say here that these two triangles, the small and big one around the outside, are similar due to angle. Alright, so kind of just made up another example there on the fly. Over here, I have changed the orientation of these triangles. We want to verify that they are similar, or see if they are. And let's keep our ratios going left to right. Just, I don't know why I decided to say that. And how am I going to set up my ratios here when the triangles are not in the same orientation? And I'm not being told to, is triangle blah 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 similar to triangle blah blah blah. I don't have like a name here to kind of guide me to how to set up my ratios. Well, I'm going to match up the largest side. So 15 is the largest side of this triangle, and 11.7 is the largest one here. So 15 over 11.7. You're not really technically supposed to have decimals. Like if I were going to write this as a final answer, you're not really supposed to have decimals inside of a fraction. I would have to fix that somehow, maybe multiply top and bottom by 10 to move the decimal over. But we're gonna divide them and make decimals anyway. So we're matching up the largest, going left to right. Let's see. Probably the next easiest one to figure out is the smallest. We have 9 as the smallest side here, and 7.2 is the smallest here, so we're going to do 9 over 7.2. I need to put question marks over those equal signs because I don't know if they're equal or not. And then we have the middle side of 12 being matched up with the only thing left I haven't used yet, which is 9.6. If all of these are equal, then we can say that the triangles are similar due to side, 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 but it's going to turn out they're not. 15 divided by 11.7 is 1.282, and these other ones are equal to 1.25. Now, I made two of those ratios the same on purpose because, well, even myself and sometimes my students are a little bit lazy. So, they might look at something like this, they might, test a couple of the ratios and go, okay, I got the same answer, they must be similar. You need to make sure that it is called the side, side, side theorem. All three ratios have to be the same. That one is not. These two triangles are not similar. Alrighty then, we're going to solve for x. Now if you look right here, I'm telling you that these two triangles are similar. I'm not going to be looking to see if these are similar. I'm told that they're similar, and I want to use that fact to solve for the unknown value of b. Well, if these two triangles were congruent, then, and I've kept these in the same orientation, by the way. So if I told you that these two triangles were congruent, solve for b, we would just do b plus 2 equals 6. I probably wouldn't have the unknown value of b in two places. But these are not congruent triangles, they're similar triangles. And if they're similar triangles, then looks like we need to have side, angle, side. So they're similar to the SAS theorem, if you will. Or at least that's the information I have in the diagram. So I need to set up equal ratios, kind of going back to our previous video of similar polygons. I want to set up equal ratios to solve for the unknown value. So let's say we're going to have b plus 2 over 6 equals 2b minus 1 over 8. And again, we're told that these are similar, so we should have equal ratios, and that fact that, knowing that these ratios or these proportions must be equal allows us to solve for b. We're going to cross multiply this. You can cross multiply to solve equations anytime there's only, there's one variable on the left and one variable on the right. That's what we have. So we have 8 times b plus 2 equals 6 times 2b minus 1. Afraid I might run out of room here. We're going to distribute through the parentheses, so we have 8 times b and 8 times 2, which is 16. We have 6 times 2, which is 12. And 6 times negative 1, which is negative 6. You can't solve for a variable when it's on both sides of the equation, so we're going to subtract 8b from both sides. You should be able to solve equations no matter what side of the equation the variable is on. If you tend to get the answer right more often when you have the variable on the left, then maybe you'd want to subtract both sides by 12b and allow your answer to come out to be negative. I'm trying to avoid a negative if possible, so I'm taking my 8b to the other side. And I'm also running out of room, so let me I don't like to do this, but let me do a couple of steps at once. I'm going to have 4b over here when I'm done, so I'm going to move my b's to the right. So because of that, I want to take this negative 6, and add 6 to both sides of the equation. that should allow me to finish this. 16 plus 6 is going to be equal to 22. We have 12 minus 8, which is equal to 4. We want to finish solving this for b, so we're going to undo this multiplication of 4 by dividing, and we get that b is equal to, now this is not going to divide evenly, and I don't want a decimal, so because they're cheap, right? So let's see here, 4. How many 4s can we get, whole values of 4 can we get into 22? Well, 4 times 5 is equal to 20. Okay, 20, this is 22, so I take 20 out of 22, I get a remainder of 2. So we have 5 and 2/5 is our final answer for B. Let me check. Excuse me, I divided by 4. Okay, so our final answer is going to be 2 divided by 4 is 1/2. So our final answer is 5.5 for our answer of B. That is the end of my video. I'm Mr. Tarrou. Bam! Go do your homework.